the plan for today, we are going to complete this lecture note, and then we're gonna move to the next one, which is polar coordinates. And that would be the last handout for integration chapter. And then after that, we're gonna learn differential equation next week. All right, so let's look at example 51 first. This is the one that I stopped at last time. So this example, I asked you to sketch the region of integration, and then I asked you to switch the order of integration from dx dy to dy dx. Well, hopefully you see the point for this example that the picture is not given at the first. Well, you have to draw a region of integration from the given integral. And last time we showed you that, hey, if you have the given integral here, you can draw a region of integration like that. And once you get the region of integration, you can switch the order. Well, the technique is that you just switch from using the horizontal line that we have in the question. We switch it to use the vertical line instead. And you see that the work is not easier because if you use dy dx, you get two terms here. The reason why you get two terms is because when you draw a vertical line, you're gonna get the region that, well, on the orange part number one that we have here, you're gonna see that this is from x equal to 0 to x equal to 4. Well, you're gonna draw a vertical line, and your line that you have, you're going to start from line y equal to 0 to the line y equal to 3 over 4x. And here, y equal to 0 to y equal to 3 over 4x. That means on the first part here, or first piece here, well, you're going to start from 0 to 3 over 4x. And then on the second part, on the pink one, you're going to start from y equal to 0, and then it hit the circle all the time. So that means you're going to start from 0 to that circle, and that circle is x squared plus y squared equal to 25. And if you simplify it, you're gonna get y equal to square root 25 minus x squared. And your outside boundary is gonna be 0 to 4 on the first term, because on the orange area I start from 0 and end at 4. And then on the pink area, I start at 4 and then I end at 5. Well, that would be a good example to practice for switching the region of integration. All right, so we have one more example. Example 52, this is the last one for this handout, and then we can move to polar coordinates. Yay. All right, so let's look at example 52. All right, we have the question ask you to sketch the region of integration and set up the double integral. So let's look at that. Well, we have S. This is the region bounded by lines. So you have three lines: y equal to x, y equal to negative x, and 2x plus y equal to 3. You have to draw the region first. The question says sketch the region, and then you set up double integral using the order of integration dx dy or dy dx. So let's do that. Well, first of all, you need to draw a picture. Yes, so we're gonna do the picture here. So I have y equal to x. This is our first line. So y equal to x is here. And then the second line, I have y equal to negative x, which is going to be, the same graph with y equal to x, but it just reflects, to the negative part, which is this one, right? Everyone know how to graph it, I think. Oh, this is basic algebra. So this is y equal to negative x. So you just get two graph here. The graph number 3, this is going to be the purple one, 2x plus y equal to 3. This is still a line. However, well, raise your hand if you cannot graph this one. Anyone have a hard time to graph this? So 2x plus y equal to 3. Well, the trick to graph this one is just, well, this is a line for sure, but well, if you see, this is the same thing with y equal to 3 minus 2x, right? This is a negative slope, so it's going to be the line with negative slope. Well, the easiest way to graph this thing quick is you find the intercepts, and then after that, you draw the line. So here you can see that when x equal to 0, you're going to get y equal to 3, right? And then when y equal to 0, x is going to be 1/2. So that means the graph gonna pass the point x equal to 0, y equal to 3, and x equal to 0, 1/2, and then 1/2, and then y equal to 0. So the graph gonna be like that, right? The graph. Well, at some point it's gonna cut. Well, you know, I didn't use a ruler, so but that is a lie. But you know, I didn't use a ruler, so it's a little bit off. This is just not a proper scale, but yeah, we got the line. This is the line that we have. So the purple one is line number 3. The blue one is line number 2, and the red one is line number 1. Does it make sense? So the purple line here gonna be y equal to 3 minus 2x. Well, we need a picture because once we set up the integrals, we need the picture because we want to know what area we integrate with respect to. Well, after you set up the picture here, that's your first step. Well, you get the region. This is the region bounded by these 3 lines, the thing that I highlight in yellow. All right, so, well, you can see that if you want to feel more comfortable with this thing, you could find the intersection first, right? Because you know that the intersection here at the origin is 0, 0. And well, the red curve, the red line and the purple line are gonna cut at one point here too. What is going to be the intersection here? So you can think you have, if you have line y equal to x and line y equal to 3 minus 2x, you can find the intersection. And that intersection is gonna be this point. Well, you need to know that number anyway, right? Because when you set up the integral, when you set up the integral, you need that number. Well, some of you already got it. So Nida and Shuri, well, yes, right, 1, 1. Well, if you don't know how to solve for that, you just set 2 equations equal to each other and solve. Well, I will do it quick here, and then you solve, you get x equal to 1, and that means y equal to 1 too. Well, this is 1, 1. So the same thing with this, the other intersection here. On the bottom, so you have y equal to negative x and y equal to 3 minus 2x. Well, once you set up the equation, you're gonna get, I think, x equal to 3, right? And then y equal to negative 3. All right, so well, that is your intersection point. Now your answer is gonna be what? So let's look at your answer. Well, this is the last example for this handout. So at this point, I expect you to do this question fast. So integrate. We're gonna start by using the x dy first. Well, let's look at the x dy. Well, again, if you want to use the x dy, what happened? So we're gonna use the x first. That means we're gonna integrate with respect to x first. Well, that means we're gonna draw a horizontal line, right? Because we're gonna cut along the x-axis, which is here, the x first. Remember my technique. The x first means you cut along the x-axis first. Well, here you can see that, unfortunately, you're gonna get 2 parts. So part number 1 is going to be the part that you draw a line from the red one to the purple one. And the second part is going to be the part that you draw the line from the blue one to the purple one, right? That. So that means you have no choice. You have to split the integral. Does it make sense? So the first part, well, I'm gonna do from the bottom to the top. So the first part gonna be, well, start from here. You just keep going. Well, at this part, good. It's go to the from the blue line to the purple line. So, well, if you wanna go slow, this is blue to purple, and then that is red to purple. And then you can see that from y equal to -3 to y equal to 0, you start from blue to purple. And then from y to 0, or from y start from 0 to 1, you're gonna do the second one. And then you just use the blue one, which is the blue one. This is y equal to -x. So that means this is x equal to -y. The negative y here come from the blue line, y equal to -x, I mean x equal to -y. The red one here, it's just y equal to x, that means x equal to y. So the purple one is a little bit tough because you have y equal to 3 minus 2x. That means x equal to, let's see, 3 minus y over 2, right? Because you just need to switch the, the equation. So it's just 3 minus y over 2. Well, hopefully you, at this point, you feel like it is not hard for you because, well, this may be the 10th example already. So that is the x dy. And, you can do the same thing with dy dx. Well, do we have to split the region? Well, you can see that to answer that question, you can look at that, right? Well, again, no choice. You have to split the integral because from 0 to 1, you're gonna start from the blue one to the red one. And then from 1 to 3, you're gonna start from the blue one to the purple one. So that means from x 0 to 1, you're gonna do one thing. And then from 1 to 3, you're gonna do another thing. So from 0 to 1, you start from the blue one, which is -x. And then you're gonna go to the red one, which is x. And then from 1 to 3, you're gonna start from -x, and then you're gonna go to 3 minus 2x. Well, this is how you set up the integration. Sounds good? Well, any question for this example and the whole part of switching the order, the x dy, dx? All right, any question? What will have me that? So if the boundary is just number, we can switch them. Yes. So if the boundary is just number, you have no problem to switch them at all. So let's look at practice problem here. If you wanna feel like, hey, Ajahn, I need more practice. Well, example 53 here, you can see that the pattern of example 53, they ask you to integrate this. And when you have answer to NIDA question, well, you see that you have 0 to 2 and 0 to 4. Well, when you have that, it means the domain is rectangle. And this is the same thing with integrate. The same here. The x dy, x from 0 to 2 and y from 0 to 4. This is the same thing. You can do either the x dy or dy x like that. Well, this is acceptable because the domain is rectangular. Right, so as long as you see that your domain here is just, hey, it's all number, they are all numbers. Yeah, you're good. That is just domain rectangular. This is the easy case. Well, this is rectangular one. This is rectangular one. Well, this is not rectangular, but I think it's easy to integrate because you integrate dt first. That means here it's gonna be constant. You can pull out, and then something gonna get canceled, and then you can integrate easily. Well, example 54, this is the same thing with what we just did on the previous one, example 52. So you have a region D that you have to draw a picture first. Once you draw a picture, they ask you to set up the integral. Well, you pick the one that you want, easier order. You can pick the x dy or dy dx, whatever you want. Well, if you pick the x dy, you draw a horizontal cut. If you pick dy dx, you do a vertical cut. Does it make sense? And this is just evaluating. Well, you know, sometimes like question 55.2, 55.3, you need to how do I say, you need to switch the order of integration, because here you can see that there's no way you can integrate e to the x to the fourth power with respect to x, right? Because you no clue, you have to integrate that thing. Even you use integration technique by part or something, that's no way you can do that. So you have to switch the order of integration. That means you have to draw the picture and then you switch the order of integration. Well, this is the question that you need to practice. And that's all for this chapter. You know, integration into dimensions for using the x dy. All right, so we're gonna spend more time on integration, but we're gonna talk about polar coordinates. Well, first of all, I am going to send the handout in the chat, so you know that we have a new handout here. Well, you can download from Blackboard too, but I know some of you love to get the handout from the chat here. So I just send you the new handout in the chat. We're gonna start the new topic, polar coordinates, in few minutes. So if you have not downloaded, please go to Blackboard to download it. All right, so we are going to look at double integral in polar coordinates. Well, this is the idea. So before you have integrate the x dy and dy dx, don't you think that we should have another way to integrate other than the x dy and dy dx? So, well, mathematicians, they think that, hey, well, let's suppose that you have the region like this is y, this is x, and suppose you get a circle, right? Once you get a circle here, well, suppose this is the circle x squared plus y squared equal to 1. And then suppose that you have the line here and the line here. And then your region of integration is the one that I highlight in orange here. Well, if you use dy dx, you're going to do the vertical cut. If you do the x dy, you're going to do a horizontal cut. Well, the idea of polar coordinate is we're going to define another coordinate. So we can do a cut like that here. You know. So if you do the cut like that, it is going to be a lot easier, right? Because you don't have to split the region as all. Well, if you do the cut start from the origin point here, and then you go to the back line, you know, diagonally, I should say, it's just like that. This is going to be the idea of polar coordinates. So we're gonna construct a polar coordinate, and we're gonna use it to set up double integration. All right, so let's do it. Well, first of all, well, how many of you have heard about polar coordinate before? Answer in the chat, please. Yes or no. Have you heard about polar coordinate before? Yes or no. Nida said no. All right, Shuri, yes. So I mean, I think some of you say yes, some of you say no, but mostly gonna say no, huh? Okay, because you know, I think majority of the class have not seen it before, so we're gonna go slow for this part. So for the polar coordinates here, so well, compared to the rectangular coordinates that you have, the polar coordinate, you're gonna have the origin point, which is called pole. It's gonna call pole. This is the same thing with the origin. Well, on the rectangular coordinate, you're gonna have y-axis and x-axis. This is the rectangular coordinate that you have. You know, in your high school, and this is the thing that this is the most common thing in this world. But if you want to use polar coordinate, this is going to be the one that you have the pole here, the origin, the same origin, but the axis is going to be just the polar axis. This is the polar axis here, and that is the polar coordinate. And then to get the polar coordinate point, you're gonna use the order pair as well, but your order pair gonna be r and theta. Your order pair r theta, your r here gonna be your radius, your theta here gonna be your angle. So the way we're gonna use the polar coordinate is, well, we're gonna specify the point by using the radius and the angle. So for any point, if you have the pole here, and if I have the polar axis here, for any point here, suppose I have the point here, the point r theta here. So we're gonna say that this point r theta is the point that we have the radius r from the origin, and the angle that we have, well, starting from the polar axis, and then you do the angle theta starting from the polar axis. You do the counterclockwise direction, and then you get theta here. That means your point here is going to be the point r and theta. Well, that is the polar axis. So to give you an idea of the polar coordinate here, we're gonna do example here to show you how to plot the points into the polar coordinate. So look at the graph here, polar coordinates. Well, again, you're gonna have the pole here, the laser here. This is a pole 0, 0. Well, in rectangular coordinate, this is 0, 0. But in polar coordinate, this is just a pole. And then the polar axis is here. This is the polar axis. The polar axis is going to be equivalent to theta equal to 0. Well, if I want to plot the point, so let's start it. Let's start by A. If I have A 1 and 3 pi over 4, well, in the plot, you're going to have radius 1. And you have to have theta equal to 3 pi over 4. So that means you have radius 1 and theta equal to 3 pi over 4. So you have to start from, well, this is the polar axis, and you turn the counterclockwise 3 pi over 4. All right, go here. 3 pi over 4 is gonna up to that. Well, this is the axis 3 pi over 4. And then you just start, once you know that this is a 3 pi over 4 here, you move one step from the pole. And this is the point A. Does it make sense? Well, it's going to be on the line 3 pi over 4, but you move one step from the point A. Well, for let's do C first. C is 2 and pi over 6. Well, this means you start from the angle pi over 6, which is, you know, the pi over 6 axis, and then you move 2 steps on the positive side of pi over 6. Well, this means pi over 6 is here, right? Pi over 6 is there, and then you move 2 steps. So this is the point B. Well, just from the pole, you just take 2 steps, 1 and 2, and that will be your point B. And then your point, not B, sorry, C. So the point B is a little bit tricky because you have -1 and pi over 4. So you look at pi over 4 first. Instead of moving, you know, moving forward 1 step, you just go in negative direction, -1 step. So pi over 4 is here. Once you move negative 1 step, you're gonna get this point B. Good. And then the point D here, look at 5 pi over 6. Where's 5 pi over 6? Here. 5 pi over 6. And then you move negative direction, like 1 step. So you're gonna get here, this is a point D. Well, this is the simple one, just to make you more comfortable with polar coordinates.
I'm sorry.
Any questions?
I have a question.
And I go for it.
For point B, aren't you supposed to put it at 5 pi divided by 4?
Let's see. Oh, okay. I missed. Thank you, Shruti. So this is the point B. Sorry, the point B is, well, here. 5 pi over 4 is different. I mean, it's opposite to pi over 4. So this is must be 5 pi over 4. Thank you for correcting me. So I mean, I made me test sometime because I went too fast. But yeah, that's a good point. And then the last one is E is 5 pi over 12 and negative 3. Well, this is going to be that one, right? And then going 5 pi over 12, and then you go back 3 units. All right, so that this is called the polar coordinates. You can see that. Well, one thing that is hard about polar coordinate is you can see that for one point in polar coordinate, you can have more than one representation. Let's say the point B here. The point B here is negative 1 and pi over 4 here, which is going to be this point. Well, some of you are going to say that this is the same thing with 1 and 5 pi over 4. Yes, it is the same thing. And this is the same thing with negative 1 and 2 pi plus pi over 4. Yeah, the same thing. Well, because as long as you go to pi, the angle, you add 2 pi to it, it's going to come back to the same angle, right? And then because this is the circle. Well, the way we think of theta is just once we get 2 pi, we come back to the origin, and then another 2 pi, we come back to the origin, and then it's like trigonometric function. You can just go back again and again and again. So that means you have more than one representation for the point. That is the thing that polar coordinate is a little bit harder compared to rectangular coordinates. All right, so well, we're gonna look at the relationship between the polar coordinates and the rectangular coordinates, because some of you are gonna say that, hey Ajahn, I know this is the point C 2 and pi over 6, but what is going to be the similar point here, the same point here on the rectangular coordinates? Well, if I put the y-axis here and then I put the x-axis here, so what is the coordinate here on the rectangular coordinates? So let's look at the relationship between them. So in order to get the same point, x, y, in x, y, this is in rectangular coordinate. R theta, this is in polar coordinate. Well, if you have the same point here, x, y, and r theta, in polar coordinates, you're gonna get the radius r here, right? This is the radius r, and this is your angle theta. That is in polar coordinates. But in rectangular coordinate, you're gonna have x here and y here, which is just regular how to measure x and y in rectangular coordinates. The distance here called x, the distance here called y. So you can see by Pythagorean theorem, right? It's gonna be x squared plus y squared equal to r squared. And then by the ratio of trigonometric function, you're gonna get sine and cosine and tangent here, because sine is opposite over hypotenuse, right? So well, once you look at sine theta, this is the opposite side, which is y, over the hypotenuse side, which is r. Well, that is basic trigonometric function, and then you're gonna get y equal to r times sine theta, x equal to r times cosine theta. So to sum up, if you wanna switch the point or the equation between polar and rectangular coordinates, so the thing that you have to memorize, r square equal to x square plus y square. That's the first one. X equal to r times cosine theta, y equal to r times sine theta, and tan theta equal to y over x. If you can memorize this thing, well, you can switch the polar coordinate and rectangular coordinates. For example, on the previous slide, we have the point C, which is 1 and 2 and pi over 6 here. This is the point C. Well, this is in polar coordinates. Well, you can get this the value of x and y in rectangular coordinate as well. So this is your r, right? This is your theta. So x equal to r times cosine theta. So x gonna be 2 times cosine pi over 6. And cosine pi over 6 is 3 pi over 2. Not 3 pi over 2, sorry. Cosine pi over 6 is square root 3 over 2. Well, square root 3 over 2. And then that means you get x equal to square root 3, and then y equal to r times sine theta. And then that means 2 times sine pi over 6. And that is going to be 2 times 1/2, right? And that is 1. So that means the same point here, point C here. If you want to write it in the polar coordinates, you're going to get 2 and pi over 6. If you want to write it on the rectangular coordinates, it's going to be square root 3 and 1. Make sense? Well, that is how we think of polar coordinate and rectangular coordinate. Well, the same thing if you, let's look at that one. So if you have the point in the rectangular coordinates, let's say the point 3 and 3, for example, 3 and 3. What is going to be, this is your x, this is your y in polar coordinate. What is going to be your polar coordinates with respect to this point? So you can think, hey, if I want that, I know that r square is x square plus y square, which is 3 square plus 3 square equal to 9 plus 9, 18, right? And then r is going to be square root 18. And then square root 18, this is 3 square root 2, right? And then also you have tan theta equal to y over x, which is 3 over 3, and then that is 1. Tan theta equal to 1, that means theta equal to pi over 4, right? Because tan pi over 4 is 1. That means if you want to switch the point 3, 3 to the polar coordinates, this is the same thing with the point r equal to 3 square root 2 and theta equal to pi over 4. Make sense? That is how you switch. This is going to be your r, this is your theta. Switch the point from the polar coordinate to the rectangular coordinate. So give me the point in the chat. How comfortable you are with polar coordinates now. Out of 10, how you comfortable with polar coordinate now? So give me the answer in the chat, please. Out of 10. Okay, good. Well, if you get more than 9, I think yes, you understand, right? So the polar coordinate, it's just another coordinate. It's just, well, but the way we measure it, we're gonna use r and theta. All right, good. Well, keep me post in the chat because I check it. Well, because at the end of the class, I get your attendance from the chat. If you have not put anything in the chat, I don't know you are in for the class. All right. So next is well, once we transform the point, we can transform the equation too. So let's look at the equation. Well, let's say, well, the polar coordinate is going to be super helpful when you have the circle, something that polar coordinate, because you can see that the polar coordinate is just r and theta, so it's going to be a lot easier to work with circles in polar coordinate. So let's look at the circle here. You have x squared plus y squared equal to 4. This is just the circle, right, with radius 2, right? The origin going to be at 0, 0. Well, from your basic math skill, hey, this is the circle and radius 2. Well, the rectangular coordinate, you get x squared plus y squared equal to 4. For polar coordinates, so what it's going to be your equation for in polar coordinates. So because you know that x squared plus y squared is equal to r squared, right? So the equation for the circle is r squared equal to 4. Or it is I equal to 2, or it is I equal to negative 2. You can use I equal to 2 or I equal to negative 2. Doesn't matter. So let's say I use I equal to 2. Well, the equation I equal to 2 in polar coordinate, it is a circle. Why is that? You can see that, hey, if you have the pole here, and if you have the polar axis here, well, if I want I equal to 2, it means I can draw the line I equal to 2 and no restriction on theta. So it just keep going. And then, yeah, this is a circle. You can see that the circle in polar coordinate, the equation is a lot easier compared to rectangular coordinates. Make sense? Well, that's pretty simple. And then you can see that, well, this is the circle as well. Circle. Well, but this is a little bit tough because you have 2x here. So the origin is not at 0, 0. Well, you can see that in the rectangular coordinates, the equation looks a little bit messy because, well, if you try, you're gonna get x squared minus 2x plus y squared equal to 1, and you're gonna get x squared plus 2x minus 2x plus 1, and then plus y squared equal to 1 plus 1 here. So I add 1 on both sides, and this is x minus 1 squared, and then plus y squared equal to 2. Well, actually, this is a circle with radius square root 2, and the origin going to be at 1 and 0. You can see that this equation is not simple in rectangular coordinate because it looks a little bit tough that you need to simplify it. But once you look at the polar coordinates, so let's see what happened. It is just r squared, right? Because r squared is x squared plus y squared, and then x is r times cosine theta. From the previous slide, x equal to r times cosine theta. If you cancel r on both sides, you're gonna get r equal to 2 times cosine theta. Simple like that. So you can see that the circle in polar coordinate, the equation look pretty simple. R equal to 2 times cosine theta. This is the circle in polar coordinate. But in rectangular coordinate, the equation looks more complicated. Well, that means when you look at the question and the question asks you to work with circle, you should do the polar coordinate. I mean, you should think of switching to polar coordinate because this is going to be a lot easier way to set up the problem. Well, that is the key idea for today and for this part. And now we can look at the x plus y equal to 3 and y equal to 1. This is the same. Oh, this is a simple one in rectangular coordinate. But when you do the, oh, I will come back to the answer in the chat. 1 second. Let me finish this thing. So when you do the line in rectangular coordinate, it's easy. But when you do the line in polar coordinate, it's gonna be a little bit tough. You look at that. Y equal to -1. This is so simple in rectangular coordinates because this is y equal to -1. So simple, right? It's just the horizontal line here. But now in polar coordinates, you're gonna have r times sine theta equal to -1, and that means r equal to -1 over sine theta, and this is r equal to negative cosec theta. Oh my God. Well, y equal to -1. This is similar to y equal to r equal to negative cosec theta, which is well, if you want to work with the line, well, we prefer to do the rectangular, right? Because y equal to -1 looks so simple, but once you switch to rectangular coordinate, it looks a little bit tough. Well, even x plus y equal to 3 here. Well, this is r plus r cos theta plus r sine theta equal to 3, and that is r equal to 3 over cosine plus sine. Well, the equation that looks pretty simple in rectangular coordinates here, it looks a little bit complicated in polar coordinates. R equal to 3 over cosine theta plus sine theta. All right, so the idea of this part is I want you to get the idea that, hey, if you want to work with polar coordinates, everyone, well, when you see circle, well, you have another way to do the question because you can switch to polar coordinates, and that's gonna make your integration looks more clean and simple and easy to integrate. So I will look at the question in the chat, please. Can you explain the part with two cosine? Okay, you got it already. Good. So the idea is just this is a thing that you have in your mind. This is the relationship between polar coordinate and rectangular coordinate that you need to use it when you switch it between them. Okay. Well, we're gonna give you a break, but before we give you a break, let me give you the idea here. Before the break, I will give you the idea how to integrate in polar coordinates, and then once we come back from the break, we're gonna do examples, and that is all for today. All right. So the idea in polar coordinates, well, it's gonna be useful when you have a region R like that. You can see that if you do, well, let me show you one more time. Step one, you have three ways to do it now. Number one, if you choose to do dy dx, what happens if you want to choose dy dx? Look at that. If you want to choose dy dx, that means you have to draw a vertical cut on the horizontal line here, right? What happens is some part you're gonna start from this line to that line. This is the first piece. Some part you're gonna start from this line to this line. Right? This is, well, if you want to integrate using dy dx, you have to cut into two pieces. This is number one. This is number two. Hard. If you want to use the x dy, okay, I want to use the x dy. That you can see that, hey, on the green part, I do the horizontal line, but on the purple part, you have to split the region anyway, because that to that is one part, and that line to another line here, this is perhaps part two. Still hard. You have no choice because one and two, well, if you don't know polar coordinates, this looks hard because you have to split the integration anyway. What if you use polar coordinates? So the idea of polar coordinate is we're gonna do this, everyone. Just do this way. Well, we're gonna instead of using the horizontal or vertical line, we're gonna use the line theta equal to something to be a cut, which is that. You don't have to split the region at all, because when you do it, you're gonna do here to here, 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 and then just keep going. No need to do the cut. And the order that we're gonna use are the theta. This is the theory part. So the idea is, well, we're gonna give you the formula first and do the example first. For the proof, if you want to look at the proof, talk to me, because I skip the proof part because I think this is just a calculus. This is not the class that you have to look at the proof. Well, if you want to know the idea and the proof, well, you can email me and we can chat more about that thing. But the idea for polar coordinate is we are going to set up the integrals, and we're going to use r, dr, d theta instead of using the x dy. We're going to use r, dr, d theta. And the way we're going to do for this integration, we're going to cut the point by using the line theta here. And the bottom curve going to be this, and the top curve going to be this. And that means, well, you have to integrate dr, r from a to b. And then you have theta from alpha to beta here. This is theta. Well, look at this picture. Well, you have theta equal to alpha, theta equal to beta here. And then you have I equal to A here, I equal to B here. Well, if you want to integrate with respect to this thing, so you can do that, do that, do that, do that, do that, do that, do that. So it means you're gonna draw the line theta from alpha to beta, and your top part gonna be I equal to B, your bottom part gonna be I equal to A, and you're gonna get just one integral here. Do not need to split it. In general, if you have the curve r equal to h1 theta, r equal to h2 theta here, and you know that you have to integrate from this line to this line, it's going to be just, hey, we just integrate r from the bottom curve here and the top curve here. Well, you're going to integrate r dr here, you see, r from h1 theta to h2 theta, and your theta is going to be alpha to beta as well. This look pretty abstract, I know, but once you come back from the break, we're gonna just hit the example, and you will get better when you look at example. All right. I will give you a 10-minute break. So we want to come back at 11:05. We're gonna do example, which we have 5 example. Well, 5 example that for this topic. Okay, we have a break now. Everyone's still here with me, right? Good. All right, so we're gonna look at example, but before we head to example, so let's look at the question in the chat first. So let's see what we have. If we have some questions. The first question is, we cannot switch to d theta dr, right? Yes. So here's the thing. So when we develop the theory of integration in polar coordinates, so we prove that from dA here, you can pick the x dy, dx, or r dr d theta. So the hard part for polar coordinate is you need to use this order, r dr d theta. You cannot use d theta dr. Good question. Well, this is not acceptable for that. Well, it is, yes, but the term that you have gonna be super hard, well, which is outside, the scope of for the class. But for the class, we can do only the x dy, dx, and r dr d theta. So we have to have r here as well. This is just the term that we have left from the proof. So we have to carry it with us all the time too. It's gonna be r dr d theta. All right, so let's see an example. Then I think once you see example, you're gonna get better. All right, so let's look at example 59. All right, so a region R is shown below here. I want you to decide whether to use the polar coordinates or rectangular coordinates and write the integral. Well, first question, answer me if you want to do polar or rectangular. That's the first one. The second one is, can you write the integral as an iterated integral? So that means you write double integral with respect to this region R. Okay, so number one here, do you want to use rectangular or polar coordinates? So in the chat, please. Number one, polar, right? Because some of you say polar pretty quick. That's a gear. Yes, polar. Everyone agree? Polar coordinates, right? For this. Well, the reason why if you answer polar coordinate, you can see that the reason why you pick polar coordinate, this is because the region that you have here, it looks like a circle. And well, you have 3 ways to do it, right? If you use polar coordinate, it's going to be, look at my laser here. If you want to use polar coordinate, it's going to be that. This is polar coordinate. If you use dy dx, this one, not easy. Because if you use dy dx, you split into 2 pieces. The first piece is when x is negative, circle hit circle. And then the second part is going to be the x-axis hit the circle. Not easy. And then if you want to use the x dy, the same thing, not easy. Right? Well, we're going to pick the polar coordinates. Good. And then my integral going to be, well, before you use fxy, right? Here you can say this is going to be f. X is going to be r cosine theta. Y going to be r sine theta. Well, this is just my x and my y. You know, because the relationship between polar coordinate and rectangular coordinate is like that. And then the order that you choose going to be r, dr, d theta. Simple like that. And then r going to be from where to where. So look at that. R going to be from, well, R going to be from the bottom curve, which is actually 0 now, because you have no bottom curve, and the top curve going to be here, right? Because you can see that every time when you draw a line here on the polar coordinate here, you start from every line, every theta, you start from the pole, and then you hit the circle, pole hit circle, pole hit circle, pole hit circle. So actually you start from the pole, and then you hit the circle, right? And then your theta going to be from 0 to 3 pi over 2, because you start from theta equal to 0 here to theta equal to 3 pi over 2. And that means, well, and the pole is I equal to 0. So this is I equal to 0. And the circle is what? This is a circle with radius 4. So that means I equal to 4. How do I know that the circle with radius 4 is I equal to 4? The circle with radius 4 is x squared plus y squared equal to 16, which is r squared equal to 16. And that is I equal to 4. Make sense? Well, I know this is the first example. It may, you still, if you still, struggling a little bit, well, fine. But this is how we did in polar coordinates. Compared to the second part for this question, well, I told you one thing. If you can use the x dy or dy dx, do that first, because polar coordinate is a little bit harder. Well, for this question number 2, you can see that if you draw a vertical line, that is so easy. I can draw a vertical line and then done. Well, then use the y dx. Then don't do the polar coordinates, because some function it's a lot harder to work with polar coordinate. Like this parabola, maybe if you switch to polar coordinates, this equation gonna be ugly. So we'll just keep it like that. And then when you do that, you're gonna integrate fxy dy dx. Oh, I need more space, so I'm gonna move it down here. Y gonna start from y equal to 0 to y equal to 1 minus x squared, right? And x gonna be negative 1 to 1. Well, this is just so simple. We're gonna use the rectangular coordinates for number 2 here. Does it make sense? Well, when you look at the question, don't jump to polar coordinate immediately. So look at the picture first. If it is easier to do rectangular coordinate, you just keep it like that. Keep it rectangular coordinate. Like the region number 2, this is not necessary to do polar coordinates, because if you do rectangular coordinate, it just, you can solve it by just draw a vertical line. So that means y from 0 to 1 minus x squared, y equal to 0 is this line, y equal to 1 minus x squared, this line, and x from negative 1 to 1. Okay. All right. So, well, Coach Chamon say, can we do the x dy on this question, right? You can, but a little bit tough. Well, if you do the x dy, it's going to be, well, let's do that. So it's going to be this curve to this curve, right? Because you're going to draw a horizontal line. A little bit tough, I think, because y equal to 1 minus x squared. Here you have to switch it to x squared equal to 1 minus y. And On this piece, this is x equal to square root 1 minus y. This piece, this is x equal to minus 1 minus y squared here. All right. And if you want to use the x dy, x going to be from negative 1 minus y squared, square root y to square root 1 minus y here. And y going to be from 0 to this intersection point, which is x equal to 0, y equal to 1. So 0 to 1. Well, if you want to use the x dy, going to be like that. Well, this is the easiest way to do it. This is a little bit harder, but not that tough, but you just need to be expert in parabola equation. So you can, convert it back to x equal to something. Well, hopefully that answered your question, Good Shimon. All right, so we're gonna move to the next one. Number 660. All right. Let's look at that. I want to evaluate the integral, the given integral here, where D is the region bounded by these two circles, and this region is strictly in the first quadrant. Okay. When you look at this question, well, of course, you need to draw a picture. You have no choice. You need to draw a picture. So the picture is going to be like, this is my y-axis, this is my x-axis, and I have to draw the circle here, x squared plus y squared equal to 1. You should be comfortable now. This is circle with radius 1. So it's going to be circle with radius 1 here. Well, you can see that my picture, I just focus on the first quadrant because the question said the first quadrant. So I'm going to focus on just when x is positive and when y is positive. And then next we have x squared plus y squared equal to 5. This is the circle as well, but this is the radius square root 5, right? Because we have 5 on the right hand side, so radius is going to be square root 5. Oop, that this is square root 5 and 0 at this point. This is 1 and 0 at this point. And then the region that you have is the one that you just cut this thing. All right, this is the region you have. Good. Well, it's in between these two circles. It's like a ring. It's between circle with radius 1 and circle with radius square root 5. It is in the first quadrant. Everything we want. So what would you pick in the chat, please? Dx, dy, dx, or polar coordinates? What would you pick? Okay, too easy, right? So you're gonna pick polar. Some of you say polar. Yeah, polar for sure. Why not, right? Because it looks like a circle. It looks like a ring or something. Well, if you use the x dy and dy dx, you can see the problem clearly that you have to split the region anyway. So that means, well, we're gonna use polar coordinate here. All right, let's see in the chat, please. Everyone use polar coordinate. Okay, good. Polar coordinates. Well, in order to use polar coordinate, we're gonna set up the integral here. All right, to be something. When you use polar coordinate, x squared plus y squared gonna be your r squared. That's good. X squared plus y squared here gonna turn to r squared because this is how polar coordinate works. And then minus 1. And then dA, you're going to use r dr d theta now. Okay. And then, well, let's look at the boundary of r and boundary of theta. So what is the boundary of r? So r going to start from the circle with radius 1 to the circle with radius square root 5. Does it make sense? Well, this is because every time when you do the line here, like the polar coordinates, you can see that you're going to get the area that you want but the bottom curve gonna be this, the top curve gonna be this, right? Because, well, actually this is a picture you want. This is the polar coordinate cut. It's gonna be like that. Make sense? Then what is the equation x squared plus y squared equal to 1 in polar coordinates? This is r squared equal to 1. This is r equal to 1. And this is x squared plus y squared equal to 5. That is r squared equal to 5. That is r equal to square root 5. Well, that means your lower boundary here gonna be 1. Upper boundary here gonna be square root 5. This is because you have the curve, the circle curve on the bottom and the top curve on square root 5 on the top. And then theta gonna be, well, theta is easy, huh? 0 to pi over 2. Because it sits on the first quadrant. And then you just integrate this thing, and yeah, that will be your answer. You can see a lot easier, right? Using polar coordinate compared to rectangular coordinate. Because if you set up the x dy dx, you have to split the region because you have no choice. It's gonna be two regions here if you use dy dx, or it's gonna be if you want to use the x dy, oops, it's gonna be that, which is we don't want to do that. All right, so let's integrate this thing. Well, how would you do this thing? Use substitution, right? Let u equal to r squared minus 1. Well, I'm gonna do pretty slow for you. So du by dr is 2r, and then this gonna be integrate 0 to pi over 2, 1 is square root 5, square root u, and then r. dr gonna be du over 2r, and then d theta. Well, this is just technique from Cal 1. I just use the substitution. So u gonna be r squared plus 1, so I can switch my dr to du over 2r, huh? And then that I can cancel one time, cancel out, and then I pull out 1/2. Okay, when r equal to 0, then you have u equal to -1. When r equal to square root 5. Oh. Okay, sorry. Okay, one more time. When r, well, you integrate r from 1 to 5, square root 5. Well, I'm gonna look at when r equal to 1, so u equal to 0. And when r equal to square root 5, u equal to 4. So that means you're gonna be 0 to 4 square root u du d theta. Well, I switch the, I just do the substitution. This is actually Cal 1 now. 1/2 integrate 0 to pi over 2, and then u to the 1/2 you integrate, you're gonna get u to the 3 over 2 here, and then 4 0, and then d theta, that is 1/2 integrate 0 to pi over 2, and then what do I get here? So I'm gonna pull out number over there first and get 2/3 here because I have 3 over 2 on the denominator, and then I get integrate 0 to pi over 2, and then that is 4 to the 3 over 2. That is number 8. Okay, right? Because number 8, 4 to the 3 over 2. This is take square root of 4 first, you get 2, and then 2 cubed, you get 8. And then, well, the answer gonna be 1/2 times 2/3 times 8, and then times pi over 2, which is, okay, cut. 8 over 6, which is 4 over 3. Okay, good. 4 pi over 3. Well, this is the answer. Well, what when I test you on the exam or something, well, I'm gonna test you just to set up. To integrate, that is going to be the Cal 1 part. We are not focusing on the integration technique, because that I assume that you know how to do that in Cal 1. If you have enough time, you can do it. because this is a technique in Cal 1 when you integrate just substitution and something, but the technique in Cal 2 that you just add and learn more for this class gonna be you set up the problem here, because you expected that you can expect on the exam that I'm gonna ask you to set up and then done, because on the question I'm gonna ask you just set up, do not need to integrate, because as you know this part is just Cal 1. Sounds good. Well, I think we have about 20 minutes left, 20 to 30 minutes left. So we can do one or two more example, okay? Stay with me, please. Just be patient. Well, we're gonna do one or two more and then we're done for today. And then we're gonna pick up the remaining example on next Monday. Sounds good. All right. Okay, let's do this one. 61, which is this is pretty good one. So I asked you to compute the integral here, but you can see that if you do not switch to polar coordinate, it's going to be terrible, because if you want to integrate the x dy, look at that, x squared plus y squared to the 3/2. Oh my god, how can I integrate that thing? Because x, well, it looks hard. Maybe you need to use trigonometric substitution or something in calculus 1, which is, we don't want to look at technique of integration. Luckily, you can see that you have x squared plus y squared inside. This is a trick. If you see x squared plus y squared in the integrand, well, you should use polar coordinates. The reason is because if you see x squared plus y squared, you can switch it to r squared, and that would be a lot easier. Well, if I switch this thing, if I switch this x squared plus y squared to r squared, and then 3/2 here, well, even better, because r squared gonna cancel out with 3/2 over there, so you're gonna get just r cubed, and then the x dy gonna be r d theta. This is gonna be r d theta, and then you have to think of the boundary, right? And then, hey, this is just integrate r to the 4th power d r d theta. Wow, this is so easy. Integrate r to the 4, this is r to the 5/5. That's all. But if you want to use rectangular coordinate, it's going to be terrible, because you have to use trigonometric substitution. Maybe inside there, you're going to use by part again. Terrible. Make sense? Well, so we're going to doing this thing together, but well, our final decision is we're going to use polar coordinate. All right, good. Well, actually just start this one, because I think this one is just similar thing that I'm going to ask you on the exam. Polar coordinates. Okay, let's do that. Well, first of all, the hard part is we have to get this part to the picture, right? Well, we're going to do the same thing. We let D to be the region first. X is in between that and that. This is my X, right? Okay, this is my domain D. This is my domain D. It's going to be that. And Y going to be between -1 and 1. All right, so let's get the picture from this thing first. All right. Well, this thing is X. Let's look at this thing. X equal to square root 1 minus Y square. If you square root, if you square it on both sides, you get X squared equal to 1 minus Y square. Okay. This is X squared plus Y square equal to 1. Okay. Actually, this is a circle. This is looks similar for this one. It looks similar. It's a circle. Well, okay. It is just a circle then. It looks like it is a circle. Then we draw a circle. All right. Well, which is a good sign, because we want circle. This is polar coordinate. and then y from -1 to 1. So what is the region we want to integrate with respect to? So you can see that, hey, we're gonna start from, well, if you want to use the x dy here, that's mean, well, the x dy mean we're gonna do the cut along the x-axis, which means we're gonna do the horizontal line. So the horizontal line, well, if I want the region here, well, you can see that if I use the whole circle here, is this the same thing? Is this the same thing as we want in the integral? So you can see that, hey, if I look at the area that I shade in orange, you're gonna start from the left curve gonna be this one. This is the left curve. The right curve gonna be this one. So going from the left curve to the right curve, going to the left curve to the right curve, left curve to the right curve, left curve to the right curve. Your left curve here gonna be x equal to -1 minus y squared. Your right curve here gonna be x equal to square root 1 minus y squared. And then this is 0, 1. This is 0, -1. Does it make sense? And that mean, okay, the area you integrate with respect to, this is just the circle. This is just the circle. The left curve gonna be that x equal to -1 minus y squared. The right curve gonna be x equal to square root 1 minus y squared. Good, we have the region D we want. This is just a circle. So this is the same thing with r theta when r start from 0 to 1 and y and theta from 0 to 2 pi. Would you agree? Because this is a circle. This is just a circle, people. This is just a circle. Good. And then that means your integration that you want, -1 to 1 integrate square root 1 minus y squared to square root 1 minus y squared, x squared plus y squared, 3 over 2 dx dy. This is the question. So I'm gonna switch it to, well, I'm gonna switch this thing to r square here, 3 over 2, and then r d theta are gonna be 0 to 1, theta are gonna be 0 to 2 pi. And that is integrate 0 to 2 pi, integrate 0 to 1, and then r to the 4th power d theta. And then this is r to the 5th power over 5. And then r equal to 1, r equal to 0, integrate 0 to 2 pi d theta. All right, the answer is going to be 2 pi over 5. Well, once you switch to polar coordinates, your integration is super easy and you can do it in one line. Good. I put -1 2 times in the y range part. What do you mean, Shuri? So you can explain more. Oh, okay. I see that. Okay, 1 here. Thank you. Mistake. Okay, good. Correct. All right. Any questions? Anyone? Thank you, Shuri. I got that part. Yeah. Thank you for your note. Sounds good for this question. Well, if this question show up on the exam, I consider this question to be the A part. Well, just student who can do this question, you should get A. Because this is the one that this is not easy. Usually just only the good student can do it. Well, polar coordinate is the part that, this is not simple. All right. Well, one more example, okay? Well, I know you are tired, but this is 2-hour class, so I don't want to, just waste the time much. But yeah, well, the last one I promised 62, the last one, and then we stop. I hate 2-hour classes too. It just so tired. Well, the last one, and then we stop here. or do you want to just stop here and, well, I asked it, well, let's do one more there. Yeah, well, we have 30 minutes left. Oh, Shudi say, can we just complete it? Just two more questions. Okay, let's do that. Well, two more. Okay, example 62. Well, we're gonna convert the order of integration to the polar coordinates. All right, so here again, you can see that, well, you have to transform this thing to the picture first. All right, let's do it. D gonna be x, y, well, let's see this one, y from 0 to square root y minus x squared, and x gonna be from 3 to 3 over 2, 1.5 to 3. All right, good. And then now you gonna be okay with this picture. All right, y and x. So y equal to 0, you know it. And then y equal to square root y minus x squared. Okay, this is look like a circle with radius 3. Okay, we're gonna draw a circle with radius 3. Good. Okay, good. This is the circle with radius 3. Well, but actually we only need the top part because this is just y equal to square root y minus x squared. And then we need x equal to 3 over 2 and x equal to 3. All right. This is x equal to 3 over 2. X equal, okay. The scale is not that good. X equal to 3 over 2. And this is x equal to 3, right? Because this is a circle with radius 3. All right. Looks like the region that we need is this one. Okay. It's this one. Okay. Not bad. Not bad. Right? Because this is the region that we want. You know, if you want to use dy dx, it's go vertical line here. Okay, this is the part we want. However, okay, the question say, let's switch it to f cosine theta sine theta. Well, luckily we do not need to integrate for this question. We're gonna switch it to polar coordinates. Here, you have to do that. Oops, 1 second. That, and we go to that, right? Well, let's look at that. Well, you can see that every time when you draw a polar cut here, you're gonna start from the bottom curve here, which is your line x equal to 3 over 2 to the circle here, right? Because as a picture I show you before, it's gonna be like that, right? So, well, we're gonna look at the equation x equal to 3 over 2. This is the same thing with r cosine theta equal to 3 over 2. And this is the same thing with r equal to 3 over 2 cosine theta. Well, this is going to be your top curve or your bottom curve here. And then your y equal to square root 9 minus x squared. This is x squared plus y squared equal to 9. And that is r squared equal to 9. And that is r equal to 3. So 3. Well, this is going to be your bottom curve. This is going to be your top curve. Sounds good? Because when you do when you do that, it's going to be that to that. And then the hard part going to be, you need to find the intersection here, right? Because the intersection that I point, the big point here, it's going to be the thing that you can tell the range of theta. Let's find the intersection here first. Well, the intersection, we have the circle over there, x squared plus y squared equal to 9. And, x equal to 3 over 2. You can find the intersection. You're going to get x equal to 3 over 2 and y equal to what? 9 minus 9 over 4 and then square root, right? Because you just plug in everything, plug in x equal to 3 over 2 over there, and then you get square root 25 over 4. Ooh, the number looks intense, right? And then you're gonna get, is that 25? Okay, one more. 9 is 36 minus 9 over 4. And that is 36 minus 9 is 27. Okay, sorry. 27 over 4. Okay. And we need square root as well, right? And that is 2, and then square root 27. This is what is square root 27? This is 3 square root 3. Okay. All right, so that intersection point is square root 3 square root 3 over 2. This is my y, and my x is going to be 3 over 2. Which means you're gonna get your, well, a little bit hard because you need to find the theta. Tan theta is y over x, right? And then your y is going to be 3 over 2 square root 3, and your x is 3 over 2. So tan theta is square root 3. Well, actually, you can find, well, you know, when you look at the theta going to be start from 0 to this theta. Well, what are we trying to do is we're trying to figure out, well, this is going to be 0 for sure. But the question mark here, I want to find that. The theta is going to be the theta that give you the point x, y, x equal to 3 over 2, and y equal to 3 over 2 square root 3. That theta is going to be the theta that make tan theta equal to square root 3. You solve this equation, you're going to get theta equal to pi over 3. Good. And the answer is going to be 0 to pi over 3 here. All right. Okay. Sounds good. All right. And that is example 62. For example 63, well, I want you to convert the order of integration from the x dy to polar coordinates. So let's work on this problem together. So we have the given integral. Well, you can see that the inside one is dx from y squared to 1, and the outside is y from 0 to 1. Well, that means you have the domain D. This is equal to the set of ordered pair xy such that y squared less than or equal to x and x less than or equal to 1. And then also y is between 0 and 1. All right. We need to draw a picture that represents the domain D. All right, so I am going to draw the y-axis here, the x-axis here. Well, first of all, you can see that you need to graph x equal to y squared. Well, x equal y squared, this is just the parabola. Well, this is x equal to y squared, and then x equal to 1. All right, so x equal to 1 means I have a vertical line, x equal to 1. So let's say this is the green one, x equal to 1. All right, next we have y between 0 and 1. So you can see that y is equal to 0 is the x-axis. This is y equal to 0, the purple one here. All right, this is actually y equal to 0. And also y equal to 1, this is, just to give you an idea of the upper bound of, your region. This is going to be y equal to 1 is here. All right. Oh, well, that means you can get the intersection 1 and 1 here. Sounds good. Well, from the domain D, we get the region that I highlight in light blue here. This is going to be our region for D. Sounds good. Well, you can double check this is correct because, well, if you want to do the integration, the x first, so that means you're gonna draw a horizontal line, and you can see that every time you start from x equal to y squared to x equal to 1, and then your y value is gonna start from 0 to 1. All right, the problem asks us to switch this thing to polar coordinates. So that means instead of using a horizontal line, we're gonna do something like this is like a ray, right? And then you can see that if you zoom in here, you can see that, well, once you get at the pole here on the polar coordinates, you can go that way, that way, that way, that way, that way, and keep going, keep going, keep going, keep going. So every time you're gonna start from the pole and then it's go to the green one, 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 the green one. But at one point here, well, you're gonna just switch the direction. So it starts from the pole to the green one before, but now it's gonna be the pole to the blue one. Start from here. You're gonna go to from pole to blue one, pole to blue one. Well, I should just make it more, just a picture here so you can easy to see that. Well, one second here, good. And then you can see that the line that you have here, the dashed line, gonna be the line that split the region that you want to integrate with respect to into two pieces. The first one gonna be the first piece here, the second one gonna be the second piece here. So for the first piece, you're gonna integrate, well, f cos theta, sine theta, and then r d theta. So the first one, you're going to start from the pole, which is r equal to 0, and then you go to the green one. Make sense? And then after that, your theta, well, which you don't know what it is now, but you're going to start from theta equal to 0, from theta equal to something at this point, at the line here, the line that I laser it. So it's going to be theta equal to 0, which is the x-axis, and theta equal to something here in question mark. Well, that is the number one. So let's figure out what is the green line and what is the double question mark over there. So to find the green line here, so the green line is x equal to 1. So translate x equal to 1 into the polar coordinates. This is going to be r cosine theta equal to 1, and that means r equal to 1 over cosine theta. All right, we have it. So the green line here, this is r equal to 1 over cosine. Or you can say this is secant because this is the same thing, secant theta. All right, next we look at the question mark over there. So the question mark here, how can I find the question mark? So you know that this slope line, I mean, this is the line that pass the point 1, 1. So that means, well, this is the 45-degree line, right? Does it make sense? Because, well, you have 1, 1 here. If you get the x value here, y value here, you get 1. X value here, you get 1. The ratio between y over x, this is 1. So tan theta equal to 1. So once you solve for theta, you're going to get 45 degrees or pi over 4. So this is going to be pi over 4. All right, sounds good. This is the term number 1 that you have, and then you have to compute term number 2 too and add them up together. All right, so for term number 2 here, integrate f cosine theta times sine theta r d theta. All right, let's see how can I get r and theta here. For sure, this time we're gonna start from the pole, and then you're gonna go to the blue curve, the blue curve like that, right? And then you get the area at the end. So that means, hey, you start from I equal to 0, which is the pole. All right, and then you go to the blue one at the end. So x equal to y squared here. Well, if you think again, this is r cosine theta equal to r squared times sine squared. And then that means just r, this is equal to cosine theta over sine square theta. Well, if you do not simplify it, that is okay. So you can keep cosine over sine over there. So I'm gonna get cosine square over, sorry, cosine theta over sine square here. And then, well, to look at the theta values, so you can start from theta equal to pi over 4, right? Just continue from the last time over there. And then, well, it's come back to to 0 here, well, that's mean theta equal to, well, you have to figure out what is going to be your theta over there. So theta is actually pi over 2, right? All right, that is the answer. So the final answer is 1 plus 2. All right, you're done. All right, I hope you enjoy learning polar coordinates and the integral using polar coordinates. So let's stop the clip here. If you have any question, let me know in the comment. Thank you.